Thanks, Alexander. I think that's more information about H5PI than I could possibly imagine we could learn in 15 minutes.
Thank you very much.
Very good. So I'm showing my desktop, I believe. Do you guys see that?
Not yet.
Not yet. It's coming.
Wait. Okay. How about now?
Yep.
Okay. So I'm going to talk about something related to H5PI, and it's H5PID. H5PID is a Python package we developed to provide access to the HDF server through a Python interface. And I can show you a schematic of how this works with JupyterLab. We have an environment on AWS called KitaLab. And I believe Lori sent information out about how to log on to KitaLab. If you didn't get that, you can just go here and create an HDF group account and register and get a free KitaLab user account. So with KitaLab, you don't need to install any software on your desktop. Everything's through a browser. So user comes in, they logs in. Once you log in, Jupyter Hub will spawn a new container. Now this runs in a Kubernetes cluster under our AWS account. And in this container, you could do typical H5PI things with HDF5 library, like Alexander showed. But you can also use the HDF server. So this, from your container, you make REST calls to the server, and the server in turn makes writes and reads data to an S3 bucket. So I'm going to talk in vastly more detail about HDFs in my talk tomorrow. But for today, I just want to do a quick overview of how H5PID works. So let me go with that. So switching to my environment in KitaLab. So I'm in a browser. I'm connected to KitaLab. And if you want to follow along, this is under examples NCEP3. And I just took Alexander's H5PI example, and I'm going to try to do a little on the fly programming here and switch this to using H5PID, and then we can see how it's slightly different than H5PI. So I'm going to change this line from import H5PI to import H5PID as H5PI. This means I'm going to import the H5PID package, but refer to it as H5PI, which means I don't need to change much of the code that follows. Okay, so whereas before we had this system, now I have CondaForge and the H5PID package and NumPy. And now this is interesting. The H5PI version, HDF5 version is REST, because we're not actually using the HDF5 library in this case. One other code change we need here is that in H5PID, there's no concept of a current working directory, right? So the server doesn't know what your current directory is. So you always have to use a full path name. And the path home jreadey is a folder managed by the server where I have write permissions. And here we're creating a file, so I need to have a write access to that. So we create a file in air quotes. That's the file name. Here the driver was sec2, which is a native HDF5 driver. And now it's the REST driver. I'm not sure what that's about. That's the same. And pretty much everything else is exactly like with Alexander's notebook before. Except now, each time I'm making a call, it's going from my notebook environment to the server, and the server is reading or writing data to S3. And again, I'll just quickly run through all these, and you can see that you're getting exactly the same output as we did with the HDF5 library and local files. Great data set. Here's one slight difference. The low-level API that Alexander showed, the ID, in the HDF5 library, you always get a numeric ID. With the HDF server, you get a UUID. So here it's a D hyphen meaning data set, and then a UUID to identify the data set. And we can resize, create unlimited data sets, use compression. With H5PID, in addition to regular GZIP compression, we also support BLOS compression filters. And that works. And H5 dump doesn't really work, but we have an equivalent HSLS they can use. Anyway, so I just want to show the compatibility between H5PID and H5PI. Now let me switch to a different example. This one uses data from NASA from the Goddard satellite. And NASA created like one data file per day, I believe. And it can be quite bothersome, right, as a user to manipulate, thousands of files, right, if you want to do like analytics over this entire date range. So what we did is that we aggregated these files, these 7,850 files, into one HSDS file or domain, as we call it. And so again, I import H5PID as H5PI. This HS info gives you information about your server connection. So here you see the server name is HSDS for Kita Lab, the endpoint, my username, my password, my home folder again. The node count is how many server nodes are running. And I'm going to open the file. This HDF5:/ prefix is just used to indicate that we're not dealing with regular POSIX files. We're connecting to a domain on the server. And here I'm opening it as read-only. Get the idea again. Here's this HSLS. We can list all the contents of that domain. We can list the contents of a group. We can get a data set. We can get the shape of the data set. So here it's quite large. So each day is represented by these last two dimensions, which are latitude and longitude. And then this first dimension is kind of like a date indexer, right? So index 0 would be the first day, and index 7849 would be the last day of this data set. Excuse me. So the chunks here are, you'll notice it's one in the time dimension, and then the entire latitude and longitude range. And that is very efficient if we're fixing the time and getting various geographical regions. But as you'll see, once we fix the geographical point and try to access a time series, you're crossing lots of chunks, and that introduces some challenges. These are various attributes in the data set. Okay, so now, as Alexander was showing, to access data in a data set through H5PI or H5PID, you use this NumPy-like syntax. So it's the data set bracket, and then 7840 means I want day 7840 of this data cube. And the : : means I want all the lat and long values. And I put a percent time here. We'll show you how long it takes. So in this call, we're going from our container in the Kita Lab environment to the server, and the server is reading data from S3 and bringing it back again. And finally, it's being showed in my display on my laptop. Okay, so that took 1.06 seconds. And I think if we run that again, it might be faster. Yeah, so you notice the second time I ran this, it went from 1 second to 37 milliseconds. And that's because the way HSDS works, that it can cache recently accessed data. So it's kind of like the library chunk cache, but it's shared between all clients of the server. So it's quite a bit larger. And so the second time I called it, rather than going to S3, the server found it already in the chunk cache, and we could just directly download it to my client. It's about 4 megabytes for that slice. And one nice thing about Jupyter Notebooks is that you can have these inline plots. So I'll just do a little plot here, and we see it's a kind of fairly low resolution view of the Earth with this heat map for the temperature. And we can zoom in on that. That's nice. There's a fill value used, which is was -999, I believe. And it might be interesting to get all the values in this NumPy array that are not the fill value and make a histogram out of it. Let's do that. And now it's plot. So it's quite easy, right? So here you see that most of the temperatures there's few of these very cold outliers. It seems like 10 degrees centigrade is kind of the median. There's a little spike in very warm water, and then it goes down to nothing past 30 degrees centigrade. Okay, so let's again look at those chunks. So recall, I was doing HDF selections that were aligned with this chunk shape. Now if we switch that, if we're going to fix the last two indexes and pull various time ranges, we're crossing not just one chunk, but many chunks. And here, one advantage of the server is that reading multiple chunks in this way is parallelized. So the server has multiple containers running, and when you do a selection across multiple chunks, all those containers are working simultaneously to read the chunk data. So let's try this. I'll do a start time index of 0 to 500. So in this case, we're crossing 500 chunks. And each chunk, we're just pulling one data value out of, and then returning all those data values as a one-dimensional array. Okay, so that took 12 seconds, and I can do a plot. So now here, we're seeing a plot of how temperature varied for this particular geographical point in the data set over a time range from day 0 to day 500. And again, I think if we run this again, it might be faster, or maybe not. Let's try it. Maybe not. Yeah, a little faster, 11 seconds this time. The plot again, and let's see. I think this is like a sub-range of that. Well, I'm not sure what I'm doing. Oh, this is calculating some summaries. Anyway, in the interest of time, I will skip that. So I think we're already over. And oh, yeah, here's a sub-range, more detailed for that time range. Okay, so that concludes my talk. And I guess, Elena, now we have time for questions.
Thank you. We actually have, I skipped Steven's talk because Steven was busy with the cluster. Steven, can you hear me?
Yes, I can hear you.
Would you like to present, or we have time for questions and you will go later?
Probably later, because I am still busy with the...
Okay, thank you. Then, yes, let's open floor for questions for first 3 talks. And you can just type it in chat window, or Lori, we can, if you raise the hand, we can unmute you. I don't see raised hands. Or maybe I don't see them. So, Lori.
I don't think anyone's raising their hands. I believe
Anyone?
they can unmute themselves as well.
Oh, okay.
So I'll ask John something, which
Sure.
is I'm assuming that to use KitaLab in a fully operational scenario, there is a cost associated with it because you're using AWS hardware.
Yes. Well, we are paying for that cost, which is fairly minimal at the HDF group. So I'm not quite sure what you mean by operational. I mean, so it's free for anyone to log on to run a Jupyter notebook. And I believe there's like a data limit. So you get like a 10 gigabyte POSIX file drive, basically, that's part of your KitaLab environment. And then 100 gigabytes, I think it is, that we allow for creating data in S3. So if you want to do something like, say, run a class or import terabytes of data, then I'd ask that you talk to us and we can set something up.
Yeah, it was more the sort of terabytes of data thing that I'm interested in.
Mm-hmm. Yes, and of course, you know, you can, everything we have is open source, so you can easily set up your own environment to run on your own account if you have that kind of need. Does that help?
It does, thank you. Yeah. I'm interested in the caching technology as well, but I might talk to you some other time about that.
Okay. Well, I'll go into some more detail about that in my talk tomorrow, if you can catch that.
Thank you. Any other questions?
So there are some questions coming up in the chat now.
Yeah.
Oh, okay. John, can you see the questions in the chat there to everyone? From Newnham. How is the best way to assign names, units to variables in a 2D table? Is the attributes the right place to do that, and about the access property?
Right. Yeah, I guess that means what you mean by 2D table. If it's a one-dimensional data set, you can have what's called a compound type. And that's where your type consists of multiple fields, each of which could be a different numeric type or actually a different compound type. And then the names of the fields are part of the type description. And then the rows would be indexes into that one-dimensional data space.
Yeah, I think, you know, by the names, the terms that Nuno is saying, for example, variable. I mean, it seems this is more of a however is conventional for whoever people he wants to exchange data with. I mean, it's really, as far as the HDF5 itself, it's completely generic. And so, yes, the 2D table is kind of not a easy, yeah, as you said, John, table can be either compound data set with one dimension, and we talk about 2D table, it's usually a two-dimensional data set. It's not a table the way we would think of it as a table.
Yeah, with HDF5, there's many ways to accomplish the same end goal in general. And what's best tends large part on, you know, the kind of interface you're comfortable with and what your preferences are.
Yeah, and the axis property, I assume that's like something like coordinates, or, you know, like that would be also be some clarification what is meant by axis.
Right, yeah. One of the things you didn't manage to get to in your talk, Alexander, were dimension scales, which is another way to kind of assign labels to the dimensions of a data set.
Well, it's only 15 minutes.
Well, we have time, so we can discuss it a little bit more details and point, for example, share where information is.
Well, one thing I'll point out since we have time, here, let me share my screen again. So on KeyToLab again, if you log on, so I've over time, I've accumulated lots of folders, but I think when you first log on, you'll just see this examples folder. And there's a subfolder called tutorial. And there are 9 different tutorials here that walk you through basically all the things that Alexander was talking about in a little more leisurely pace. So command line tools, data sets, compression, groups and links, attributes, types, making plots, and queries. So if you're new to HDF or H5PI, it might be helpful just to walk through these. And you'll notice that if you click on one of these, that each of the notebooks starts with this use H5PI equals 1. So if you have this 1, then you're using H5PI. And if you switch it to 0, you're using H5PI-D. So most examples work with either H5PI or H5PI-D. One that's H5PI-D exclusive is this query operation. So queries are something that we've talked about for the library, but it's not part of the mainline library yet. But the idea is that you have a data set, which in this case, I call a table, since it's a one-dimensional data set with compound types. And this data set has 3 million rows. And this is what I was talking about with the type for fields. So the type here isn't just a float or an int or a string. It's a combination of a string, integer, a float, a float, a float, a float, a float. So each row in this data set represents 1 day of trading for a particular stock. And it starts in 1970. And the shape is, oh, I skipped past this part. So on this data set, we have many different symbols. And say I want to get all the rows where the symbol is AAPL. I can do this dataset.readWhere symbol equals symbol, and then it pulls back just those symbols. So this is kind of like what Gerd was talking about with the HDFQL language, but in the Python context. So the server will go through this data set and return just the rows that meet that specification. And then I can do pandas data frame and see how Apple is doing over this time span. Sorry, that was a bit of a discretion, but since we had time, I thought it might be interesting for some people.
Thank you, John.